Hello everyone. I'd just like to go through an example of a problem we were going to do in class today. Now that I actually have the audio working, you can hear me go through this example of using the speed distribution to answer some questions that we might have. So this example is related to something maybe in kinetics, like how fast a reaction will go. Because sometimes reactions need some amount of energy input through molecules colliding and hitting each other in the gas phase, and maybe that only happens at particular speeds of the molecule. So we're going to look at maybe there's some threshold, maybe it's like here, and any molecule traveling faster will react, and any molecule traveling slower will not react. So this again is a graphical depiction of the speed distribution derived from kinetic and molecular theory. And so if we want to know molecules that are going faster than a certain speed, what we want is to integrate all the area for everything above this threshold. Let's say, just to have a nice round number, let's say the molecules have to be going faster than 1,000 meters per second. And so the question is, how could we figure out what fraction of molecules is there, and how does that change as we change the temperature? So we're going to go through an example of how to do this. This is going to be similar to the example that was done in the main lecture videos, but here we're looking at a bigger range rather than just a limited range of 500 to 600 meters per second. So again, we're going to use Wolfram alpha to solve this numerically, to do the integral, because the techniques to solve an integral similar to this are pretty advanced and not even something I'm familiar with. It involves something called the error function when you're integrating Gaussians and things like that. Anyway, we're going to do it numerically, let a computer do the job for us. So again, our equation we're going to integrate, though, that we need to know what that is to put it into Wolfram alpha, is 4 pi times the molecular weight divided by 2 pi RT raised to the 3/2 power times the speed squared, u squared, and then the exponential term, e to the minus m u squared over 2 RT du. And the important thing we need to figure out here is what are the limits on our integral, or we need to integrate this from a certain speed. Well, we can just look at the range that we want. We know we're starting here, and we're going out to infinity. And so that's the range on our integral, is 1,000 meters per second to infinity meters per second, right? So we're integrating over everything over 1,000. And we can compute a definite integral from this because this goes to this is a bounded function as we go to infinity, right? So it's not just going to completely blow up. Okay, so now that we've got our integral written out here, we need to know all the parts that are going into this. So let's say we have a temperature of 450 Kelvin. Maybe we're doing a reaction at elevated temperature. And let's say we're looking at methane, reaction involving methane. I don't know what it would be. And so we can calculate the molecular mass. I'm just going to approximate it at 16 grams per mole. We can get more precise than that by using more significant figures, but we're just getting an approximate value here. And we'll want to convert that to kilograms per mole, because we're going to be using the R value that is in joules per mole times Kelvin, 8.3145. And the kilograms, just to reiterate this point, a joule is equal to kilogram times meter squared over second squared. We're doing all the speeds in meters squared, and so for the kilograms to cancel, these need a match here. And that should be everything we need to plug it in. So what I'm going to do is split my screen up here, put this over here, and Wolfram alpha here on the left-hand side. All right, so I can see the equation that we're integrating. All right, so just as a reminder, we're going to go through the syntax here on using Wolfram alpha. So if you want to do an integral in Wolfram alpha, you type integrate, right, telling it and then you tell it what function you want to integrate. So we need to put in 4 times pi, and the times use the asterisk key. And Wolfram does know what pi is, so you don't need to write out pi 3.1415 whatever. All right, then we multiply by the molecular weight, 0.016 kilograms per mole, divided by, and we make sure to divide by it, all this in parentheses, 2 times pi times 8.3145. Wolfram unfortunately doesn't know R, if we just put in R. All right, now that's our denominator. Now we have everything inside of the fraction here needs to be raised to the 3/2 power. And we need to make sure to put that 3/2 in parentheses. If we don't, what instead will happen is this will be cubed and then divided by 2, because it'll do, that's the order of operations. It'll do the exponent first before it does the division. Okay, and then multiplied by u squared times, and there are two different ways to write this exponential term over here. We can either write e raised to the, and then put everything in here, or an alternative way, and the way it's done in Excel, if we use Excel for anything, is exp parentheses, that's short for exponential, which is what we're doing here. Right, so exp minus 0.016 times u squared divided by, and we put all this in parentheses again, 2 times r 8.3145 times t 450, close parentheses again. Okay, and I do have a negative sign there. All right, and then we need to put the du here so that Wolfram knows that that's the end of the expression that we're integrating. And then we need to tell it the limits. And so we'll say integrate this function from 1000 to, we need to say which variable, from u equals 1000 to infinity. So INF is short for infinity. And if I type this all in right, we should plug this in and get an answer. And we do. And so we can also look and see that everything here matches what we have, and we can see that it does. We have the integral from 0 to 1000 to infinity, 4 pi times all of our things here raised to the 3/2 power, u squared exponential term here. And it gives us an answer of 0.233. And that means, right, so I'll put it over here. Or we could say this is 23.3% of our methane molecules are traveling faster than 1,000 meters per second. Just to show this would work, writing this out differently, if we write e raised to this, we should get the exact same answer. We get the exact same answer. It just actually writes out the exponential here, whereas before it just had the exp, but we get the exact same value here. The other thing that you can do when you have this all written out like this is it's easy to change things in this. Let's say we wanted to increase the temperature to maybe 550 Kelvin. So everywhere there's temperature, we change it to 550, and we can recalculate it. Wolfram does that pretty quick. And we should see that the fraction should increase. We can see by how much. So it goes from 23% to about 32%. We could also change the identity of the gas. We could change the limits on the integral. So once you have this typed out, it's actually pretty straightforward to compute it for different things. And so that's an example of how you have a similar problem to this in your homework, and so this is an example that you can look to as sort of a template for how to do this yourself.